So very good afternoon to all of you. We have already discussed thermal analysis, particularly the thermogravimetric analysis we have discussed in the last class. So today I will just give a brief introduction what is thermal analysis, and then we will go to DTA, differential thermal analysis, and particularly the DSC. So thermal analysis is a group of analytical technique that measures properties or property change of materials as a function of temperature. So the properties that can change include dimension of the material, mass of the material. It can also change its phase from one phase to another phase, and it could change also the mechanical behavior. So in case of thermogravimetric analysis, it examines the decomposition of material by monitoring the mass change with temperature or maybe with time. And differential thermal analysis and differential scanning calorimetry actually examine the phase change of material by the input of heat into its structure. Okay, so in general case, what is happening? So actually in absolute zero, all the solid does not have any thermal energy. It means that the atoms are static, there is no vibration or rotations of atomic bonds. So with increasing temperature, thermal energy gains in the solid will increase vibration of the rotations of atomic bonds. And when the amplitude of vibration reach to a certain level, the following change. What are the changes? Solid phase will change to liquid phase or maybe gaseous phase. You may have a gas transition, blast transition. It may melt, it can sublimate, or it may see a thermal decomposition of the material. So by using the temperature input, a thermal budget into the system, we just see different types of changes. So in thermogravimetry, we generally observe the mass change, whereas differential thermal analysis, we see the temperature difference, and whereas in differential scanning calorimetry, we observe the heat flow, and from that we try to understand the material property or material behavior. Okay, so today we'll discuss the differential thermal analysis and differential scanning calorimetry. The differential scanning calorimetry. So the heat flow between solid and its surrounding, atmosphere at certain temperature is indicated as enthalpy change. So it's a del H, which quantifies the heat flowing into or out of a solid under constant pressure. So you see, when we are giving heat input in a system, so then the enthalpy will change, and accordingly the solid phase will transform. How a solid phase alpha can change to a solid beta with its structural configuration, with the different structural configuration. It can, a glass, that means it can transform to a glass material. The solid can melt also, and then it can evaporate, or it can show you sublimation, or it may experience thermal decomposition. Okay, Abdul, you continue. I'll just record the meeting today. Okay. Okay. So commonly thermal events occurring under a constant pressure atmosphere analysis within the instrument. Okay. So what we just try to understand now, enthalpy change. Enthalpy change is nothing but the heat budget of the system is generally changed. So the internal energy is generally of a system is a sum of the heat flowing into it and the work done by the system. So if I just try to represent it in the formulation, so what del U is equal to QP minus PdV, whereas QP is represent the heat required for internal energy change under constant pressure. So enthalpy is defined by your H enthalpy U plus PdV. What is that? That means under constant pressure, the enthalpy change will be written as del H. Enthalpy change is del U plus PdV. That means internal energy change as well as your work done by the system. So once you reorganize it, you may get. So what, comparing the initial equation and this equations, we can come up with a, so del H enthalpy change equal to QP. Okay, so thus the heat flowing in or out of a system under constant pressure is equal to its enthalpy change. Okay, so enthalpy change means as the heat input of the system is changing, the property or the vibrational bond or atomic bond vibration will change, and they can change to a different maybe phase, different form, structural form, so that can occur into a material. So what differential thermal analysis and difference scanning calorimetry, the instrumental setup is more or less same. Okay, a furnace, you have a certain features in common in the instrumentation. So a furnace in which the sample is heated with a controllable environment. So we have you can see here it is a furnace and the sample chamber is there, and it is generally put in a furnace. Okay, so specific a transducer by which the property change of material is monitored. You have a transducer which is actually monitoring every parameters. Okay, and the sample is analyzed under a design temperature profile. That means either you are increasing in a specific temperature ramp, or you are giving heat input to the system, and accordingly you will try to get the change. So the temperature profile may take several forms and displayed as thermal analysis curve, and the features of the curves are related to thermal events. A constant heating rate, particularly a programming heating rate, you can observe. Okay, so that is what we observe when we put our instruments in a specific your instrumentation. So now different types of thermal analysis I have discussed. One is thermogravimetric analysis, where we just observe the mass change only. Whereas in DTA and DSC, in DTA we generally see the temperature change, you see the delta observed. Whereas in case of differential scanning calorimetry, you try to observe the heat flow into the system or out of the system. This may, it may be endothermic process, it may be exothermic process. So now what are the different parameters which actually affect our experimental conditions and the data? So if you just see properly, you can understand the sample characteristic instrumental factor. So if you see, samples have different types. So particle size of the samples, thermal conductivity of the samples, heat capacity of the system, packing density, that means the internal structure of the sample itself, swelling or shrinkage of the samples, amount of the samples, either you are taking higher sample, lower samples, effect of dilutant, what you are using as a dilutant, degree of crystallinity. That means the sample size, sample internal structure, thermal conductivity, everything is going to actually affect your parameters during the thermal degradation or thermal heat input in the system. Whereas the instrumentation factor, that means you some are related to the your furnace, some are related to the thermocouple, and some are related to the purging gas, and important is heating rate. So different thermal analysis instrumentation. So if you see here, okay, so this is a differential thermal analysis instruments where you can see it. Okay, now how the sample characteristic is affect your thermal analysis. So sample dimension and mass should be very small, so that it should accommodate the heat, and the heat should be homogeneous throughout the samples. So in the form of powder with the sample mass of less than 10 milligram are preferred. So if you take very minimum samples of 10 milligram or even less, and also the sample should be in powder form, because we have discussed earlier during the thermogravimetric analysis also that if samples are the flakes or maybe the bigger size samples, then the heat capacity or heat distribution is not homogeneous throughout the sample. That's why your program heat increase and the sample heat may not be same. So heat transfer between the samples and atmosphere will be faster in such a sample than in the lump. Thus, thermal equilibrium is more likely to be achieved between samples and atmosphere during the analysis. Sample to be analyzed should have the same thermal and mechanical history. I just told you the thermal history, and if it is a mixture, then definitely they may have the similar type of mechanical history as well as thermal history. Thermal events are affected by such history, and different results for the same chemical species are likely to be generated if the samples have different history. So the main reason for this is the thermal measurements is affected by the internal energy of the samples. If you have different mixtures and the different samples have different thermal or maybe the internal structure, they can also actually affect your data in the system. So just here we have just displayed some of your, so calibrant, you see you have a different types of your sample holder, you have a different metals, you have an inorganics, you may have an organic sample chamber, and you may have different types of sample holder. So depending on the type of the sample holder, actually you may have different advantage and disadvantage for the your thermal or maybe the data what you are trying to get. So good temperature uniformity, good thermal calibration, you have good resolution, good the determination of your boiling point, and whereas disadvantage, poor exchange with atmosphere. So if you see you are putting in a sample holder, it may not sometimes distribute the heat homogeneously. That's why sample size, the sample holder will affect your thermal analysis during the system. So heating rate, if you just go through the slides, you can easily understand the heating rate, probably the most important parameters to affect TA results. A slow heating rate is often favorable in order to approach thermal equilibrium during TA analysis. If you are heating in a very fast rate for raising your temperature, then what is happening? The temperature will not be homogeneously distributed throughout the sample. That's why you may get not the proper analysis. A fast heating rate will generate a thermal lag between the heating source and the sample. The important part here is actually the sample holder and the thermocouple is not in contact. That's why there is in between you have an inert atmosphere, and we use the purge gas to flow through it so that it should be homogeneous. So the thermocouple for temperature measurement in a TA instrument is rarely in direct contact with sample. So that's why it should be very important, so that your sample holder should be in very close vicinity of your thermocouple, and that too there should not be any heat restriction to that particular environment. So a fast heating rate can generate a temperature gradient surrounding the samples and error in measurement of samples. So you can see here this graph is of different heating rate. In different heating rate, you see the peak of your graph is shifting. So that means even here also, if you see 20 degrees centigrade per minute heating rate and 30 degrees centigrade per heating rate, you can see here you may get two graphs, but whereas in increased heating rate, you may get one peak. So that means this is very important: sample size, sample holder, then specifically heating rate, then the surrounding atmosphere. If you just see, earlier you have your sample here in your reference frame here, and here is your thermocouple. So what is happening? The atmosphere around the samples as well as the thermocouple should be easily communicable. So the atmosphere surrounding the samples start to transfer heat and supply or remove gaseous reactants or products. So whatever with increasing heat input, whatever the product gaseous materials are coming here, so that should be immediately removed from the system. So thus its chemical nature and flow affect the TA data. Flow means the purge gas or the inert gas we are flowing through it. So in most TA methods, we need an inert atmosphere to prevent the sample from oxidation reactions. So maintaining the certain rate of flow is important for TA involving a gaseous product. For example, examination of thermal decomposition. When you are having a thermal decomposition in the system, that means you have some material which are gaseous in nature, that you need to immediately remove. So now here two graphs are there. You can easily understand the thermocouple 0.06 centimeter from the center of the samples and thermocouple 0.3 centimeter from the center of the sample. That means once you have the thermocouple here, this is your temperature. So reference and sample. So your thermocouple should be properly placed and very near to your sample holder, so that you get an accurate graph for your analysis, thermal analysis. Okay. So now what ultimately the TA results can be significantly affected by experimental parameters as sample characteristics and sample holder. I discussed earlier, because you may have, so the most desirable is small samples in good powder form will be very much reasonable, and the samples should not be of different thermal or maybe thermal history, okay, or maybe the different structural form. So even so that can also affect your thermogravity graph. Okay, so heating and cooling rate. So heating and cooling rate, generally we prefer a lower heating or cooling rate, so that the heat input in the system should be homogeneous, and that should be reflected immediately to the thermocouple data, thermocouple heating rate. Okay, So atmosphere surrounding the sample, that means the furnace should be and thermocouple. Thermocouple should be close vicinity and properly placed, and furnace should be properly flowed, or maybe the surrounding should be properly put the purge gas or inert gas flow, so that all the vapors should be removed immediately, so that there should not be any barrier in between the sample holder and the thermocouple, so that heat should be immediately reaching to your thermocouple to give you the proper heat. Okay, so this is what we discussed earlier. But okay, so what is DTA and DSC? So if you see two graphs are more or less similar, but the measurement parameters are different in both the cases. So differential thermal analysis and differential scanning calorimetry are the most widely used thermal analysis technique. Both techniques have the same objective: to examine thermal events in a sample by heating or cooling without mass exchange with its surrounding. So what is happening in earlier case in thermogravimetry, we discussed the change of mass, okay, the mass changing, but here without exchange of the mass with the surrounding. The thermal events examined by DT or DSC include solid phase transformation, glass transition, crystallization, and melting. Differential emphasizes that analysis is based on difference between sample material and reference material in which the examined thermal events do not occur. Okay, so that means what is happening in most cases. So although DTA and DSC are similar in thermal event measurement and instrumentation, they are different in the following aspects. What are the difference? DTA is a qualitative technique because measured temperature difference do not provide any quantitative data for energy. Okay, so that means only endothermic and exothermic process. That means it is only there is a difference in the heat between the reference as well as. In contrast, DSC is a quantitative technique because measured heat flow provides enthalpy change in the sample during the thermal event. Okay, so that means the DTA is giving DSC is giving us more quantitative information in terms of the your enthalpy change into the system due to the heat input. So DTA can operate over a wider temperature range than DSC. The DTA can reach a temperature of greater than 1500 degrees centigrade, while the power compensated DSC, will discuss the two types of DSC are there. Okay, is restricted to a maximum temperature of about 750 degrees. This DTA feature is important for examining materials with high melting temperatures such as ceramics and some metals. So DTA is usually operated in high temperature range. Platinum and gold crucibles are commonly used. So you can understand our aim for getting the thermal analysis done. So what is the purpose of doing the analysis? Are we going for a quantitative analysis, or we are going for a qualitative analysis to understand what is happening? So that is how you need to select. Sometimes we for saving our instruments or instrument cost, we do the thermogravimetric analysis, then we put our sample either DSC or DTA for getting much better and quantitative or qualitative information. Okay, so DSC is usually operated at low temperature range, and thus aluminum pans are commonly used as sample and reference holder. So if you are using so costly, that means costly instruments are generally DSC, having very sophisticated. So the pan often need to be sealed to avoid sample mass change due to evaporation. So because what we are discussing the enthalpy change without exchange of mass in the DSC. Okay, so that's why and DSC and DTA. That's why you should be very careful about the selection of particularly the sample holder. Okay, and different sample holder actually perform differently for getting the proper data. Okay, so thermal event. Just if you observe this graph, it is you can easily see this line is actually zero. Zero means you have this zero means there is no change of temperature between zero temperature difference between the sample and the reference. Okay, so now here sample and reference materials are heated by separate heaters in such a way that their temperature are kept equal while this temperature are increased or decreased linearly. Okay, so if you see this is the measured sample temperature input, and we are getting the difference part. So both the cases, the samples and the your reference are hitting in the same rate, but now we are trying to observe the difference in the temperature between this samples and the reference. So during heating, two types of reactions can take place. One is the endothermic and other is the exothermic. Okay, so if you see this is endothermic and this is exothermic. Okay, so this is was one example of a polymer samples of DTA information. So what can DSC measures? If you see there is a lot more variation. So zero line may be along this line, but you see there is a difference in your DSC measurement also. So it can give you the information about glass transition. It can give you the melting and boiling point. It can give you the idea about crystallization time and temperature, because sometimes we increase the temperature, sometimes we keep the isothermal heating rate and we measure against the time. Okay, so and percent crystallinity you can understand also heats of fusion and reaction. That means whenever it is melting or getting fused, that also we can specific heat capacity. We can measure the specific heat capacity when a phase changes occur. And oxidative and thermal stability of a material, reaction kinetics and purity. So by just getting all the information quantitative and qualitative way, we can understand our material which we are investigating. Okay. So now what is endothermic? Endothermic, if the samples absorb some amount of heat during phase transition, then reaction is said to be endothermic. That means when it is, let's say, endo means, well, let's say here, that means it is, the heat is, it is absorbing or taking. So that means there is a difference of heat. Whereas when this, in endothermic reaction, more energy needed to maintain zero temperature difference between sample and reference. So that means what, it will take more heat, because you cannot measure it through temperature, but internal system is changing. Internal heat is required more to maintain the zero temperature difference between the your samples and the reference. Okay, so that's why melting is considered to be an endothermic reaction, because we required a heat input or maybe heat budget increase in the system, so that your all the bonds will break down and it will convert to a solid to the liquid. Sublimation means solid to the vapor, then vaporization. So that means it's a phase change from one phase to another phase. You know the structures are different in case of a solid and a vapor. That's why these are endothermic process, endothermic reactions, and that's why it required heat. It required heat, more heat, to change the system and to maintain the zero heat difference between the sample and the reference. Okay, so what is exothermic? If samples release some amount of heat during phase transition, then reaction is said to be exothermic. Okay, so in exothermic reaction, less energy needed to maintain zero temperature difference between samples and the reference. Okay, so generally the crystallization, degradation and polymerization. So in many cases, so if you see here, here is the glass transition, that means slight change in the structure. Okay, whereas if you see there is an endothermic process, that is crystallization, and again if you are coming, this is your melting. Melting means in case of it is steam melting, so it's a endothermic. In here you see in many cases the graphs are different actually. Okay, sometimes the exothermic is below and endothermic is above, so you have to see, okay, del T value, because we try to measure the difference of the temperature, okay, in the system. So here you see in the same graph, it is endothermic, below side exothermic. Here in this graph, above is exothermic, below is endothermic. So that's why whenever you are observing or analyzing a graph, you should be very careful, because different instrument setup are different. That's why we need to understand particularly what is actually in the x-axis. X-axis, you see both the cases are different. Here the x-axis is temperature. That means we are observing the DTA graph. Okay, temperature difference between your sample and reference by heating, by giving the heating. But in that case, it's isothermal heating. You see more or less the same temperature, same rate we are hitting, and we are observing in the time domain. Okay, so that is what is happening. So different types of okay. So now differential scanning calorimetry. So what is a DSC instrument? Is designed to measure the heat flow difference between samples and the reference. So whatever we discussed so far, that is actually the differential thermal analysis. That means we try to measure the difference or we are hitting in the same rate to maintain the sample and the reference frame zero value. But here the things are different. We have two different types of differential scaling calorimetry. What in initial case here, you have heat flux DSC and power compensated DSC. In heat flux DSC, what you have the temperature sensor, usually thermocouples, which are same for samples and the reference. One block for both samples and reference. So you have furnace, a separate furnace. Okay. the temperature difference between the samples and the reference converted to differential thermal analysis. Okay, so that is what we are trying to measure. So this is the sample part. Okay, so that means we are the temperature difference between the samples and references converted to differential thermal power, which is supplied to the heaters to maintain the temperature of the samples and reference at the program value. You have a specific program value. We have specific program value, and that program value, so that means our heat input to the specific furnace is different, and that is now we are trying to understand with the heat flux DSC. So to and okay, now if you see here, uh, here we have power compensated DSC. That means the platinum resistance thermocouple is used. Separate sensor and heater for samples and reference samples are used. So initially what happened in earlier case we have, but here the sample chambers and the reference chamber both are separated, and they have the separate block for samples and reference cells. Separate sensors and heaters for the samples and reference are used. Okay, so now differential thermal power is supplied to the heater to maintain the temperature of the samples and reference at the program value. So program value means at what rate we wanted to increase the sample, and for that we may require different heat input for sample as well as our reference. That's why we have two different. One is your power compensated, that means we are measuring through the power, whereas the flux compensated, where there is a flux DSC. So two are different, but okay, so again I'm just trying into elaborate way how different parameters is going to help us. Okay, so now if you see, because we have already discussed in our thermogrammetry also the same thing but slightly in different manner, but DSC and DTA are actually more quantitative DSC, and DTA is qualitative. So if you see the instruments, we discussed earlier also the furnace heating rate, recording of recording or chart speed, furnace atmosphere, geometry of the sample holder, locations of sensor, selectivity of the recording system, composition of the sample container. So we discussed earlier. So instrumental factor is also playing a big role to get your proper data. Then sample characteristics. So you see the amount of sample, that means you keep the samples very thin sometimes or very less. Nature of the sample should be homogeneous so that you can it can properly record the temperature. It should be in sample packing should be proper in your sample folder so that it should not be very tight so that the heat should not be propagated each and every places. Solubility of solubility evolved gas in the samples. That means if you are evolved gas, if it is coming out, that should be in the system itself. If it is going out from the system, then actually you are changing the mass, so it will be automatically reflected in the other parameter. Particle size we discussed about earlier. If you have a flakes or chips, it should not be proper. The powder size, specific samples will help us to get the proper data. Then heat of reaction, thermal conductivity of the samples. Actually it will be very, if the thermal conductivity is very good, immediately the heat through the furnace or through the sample holder material, it should immediately reach to your samples, and it should be properly propagated in every places. So thermal conductivity. So here what the keep sample thin. Your sample should be thin properly so that the heat should be distributed. The shape of the samples like so that it covers as much as the bottom of the pan as possible. I have shown you the sample pan actually very simple thin of different material to make the sample thin so that the it will actually it don't crash. If sample is pellet, say cross sections, that means if you have samples you cut cross sections so that it should be properly the bottom of the chamber should be properly contact with your sample. Okay, otherwise the heat properly will not properly, maybe you may have some gap in between, air gap. If powder spread evenly over the bottom of the pan and different shapes of the DSC are so what will get different types. So if you see here, okay, so sample requirement, if you see here, So one is graph through a conventional DSC, and another is your temperature modulator or temperature compensated DSC. So this initial DSC curve is giving you the first heating rate, and this is the second heating after 10 Kelvin per minute cooling. So if you see the heating and this is the cooling, so they are not following the same graph. Okay, so conventional DSC first and second heating curve with heating and cooling rate, both the cases same, but you get a different graph. Okay, here it's a temperature compensated DSC. You can see here this mixture of the two material. In that case, you are getting the information. Here is a non-reversing, where is a reversing. Okay, so many cases we are actually, due to the temperature as well, the rate will also control. Here the rate is very actually the 2 Kelvin per minute rate is heating rate is very slow. Okay, now so many problems are so involved when we are actually gathering the information or getting the information. So whenever you going for the analysis, you should be very careful and you should understand what is the system you are operated with or you are operating, and how we should get a proper accurate data. Because if you don't know the instrumentation and instrumentation disadvantage or maybe the limitations, then sometimes you will land up with a wrong data or wrong curve, which you have to deal with the wrong erroneous result. Okay, so you see here, once we hit it, this is instrument baseline. That means instrument baseline and instruments without any samples. If you hit it, it will follow this. Okay, this line. But once you put your samples, you see the sample baseline. You can get the sample baseline by connecting this point and this point. Okay, so the sample baseline on an experimental curve is the line that connects the curve before and after the peak. So you can frame a baseline of your samples by joining these 2 points. Okay, so this is accuracy of enthalpy change measurement relies on correctly constructing the sample baseline from the curve. So this is very important when we are trying to understand when it is only the instrument hitting specific temperature or specific heating rate. So you get this instrument baseline. But when you are doing with analysis, you see the slight change in the. So that may be due to so many reasons. You may not clean properly. You didn't clean the earlier study. Your samples may be there inside. So that may be the case. Okay. So now you see here a different types of graph we may get. So how to get it? So generally by various curve shapes. You see here it's a very straightforward. So what generally you need to interpolate actually the graph from this point to this point to get your baseline right. Okay. So here you see. So this is different way, and you need to see the reference material. Sometimes you need to see different understanding how to do it. It is not very unique. So sometimes people use different softwares to match the baseline or to generate the baseline for getting it, because this area is very important to get, because this is giving us the enthalpy change. Okay, so change of enthalpy. So scanning rate is also an important rate, or what rate you wanted to scan. So if you see a DSC, this is heating and this is cooling, but rate are same for 1, 2 and 3. The rate is 10 Kelvin per minute, the first graph, the second graph is 20, and the third graph is 40 Kelvin per minute heating rate. Whereas you see that there is a slight change in the graph. Okay, first case, second case and third case. Whereas during cooling, you see this is actually a polymer samples. Here you see at a low cooling rate, you see the temperature of your change is somewhere higher. Whereas in the first cooling rate, second and third, your graph has completely changed. So sometimes it is impossible to understand where actually the main event is occurring. Okay. So this is the heat effect of heating rate. So how do you determine the heat capacity of the system? Because now we are going for a quantitative analysis. Okay. So the principal heat capacity measurement is based on proportionality of the DSC response to the heat capacity. So if you remember, we have discussed about to get accurate result in your DTA or DSC, you should be very careful about your instrumentation part. So one is choosing of your proper system, then how the system operates or works, then depending on the system, you need to select your samples and your sample holder. if your samples and sample sort are not proper, then you may not be quantitative, you may not be able to analyze your material properly or characterize your material properly. Okay, so now so what is there if you just see here the determination of heat capacity. Okay, so determination of heat capacity, that means what, if you just go through it, it is your, it's a T, means we are increasing the temperature heating, and this is a dH by dt, that means with time. So if you see, this is pan only, this is pan and sample displacement, so you have a equal displacement. So the principal heat capacity measurement is based on the proportionate of the DSC response to the heat capacity. By definition, the heat capacity of material under constant pressure is the following. So Cp, the heat capacity, is your DH, thermal budget of the system, with the heat input with a constant pressure. So what is happening when we are giving heat input or heat budget in a system or maybe in a material? So I discussed in the very early stage, where it is in absolute zero, then there will be no vibration of your atoms. Okay, so once you give a heat input, they will change their vibrational bonds, and then depending on their vibrational bonds, they will break, they will melt, they will evaporate, everything can happen, and that will be reflected automatically in your DT or DSC graph. If you just see here, you see here is an empty pan. Okay, so here proportionate of heat capacity and DSC response. Okay, so you see heat capacity is also changing here system, because you see the pan heat capacity is very less only. But when you are putting pan with the samples, that heat capacity has increased a lot. And how we are giving this heat input with temperature, if you see here, this is empty pan, this is temperature, and this is T1 time, and this is T2 time. Okay, this is T2 temperature, sorry, T1 temperature and T2 temperature. So that means initially you see here is the same, that means there is, even if there is no enthalpy change of the system, but now it's a sample you are giving, so with a your maybe height 8, then this is standard, this is your standard. Okay, so standard means your two displacement is required for heat capacity measurement. So the standard is here, that means, and your sample is here. So what if you see here, you can easily understand, you have a solid, then mid, so heat capacity is a function of your heat input of the system. Okay, once you are giving a heat input, then automatically it will change. So by just calculating, we can understand how a system is changed when we are putting an heat input. Okay, so what we could do actually with the help of this DSC or DTA graph, if you just see, we could understand when the material melts, we could understand when the material starts its crystallization, and we can also observe the glass transition. Okay, so measuring transition temperature is the primary task of DT and DSC. So the common transitions are melting, glass transition, and crystallization. If you just observe this graph very carefully, so you have temperature versus endothermic and exothermic. You see there is a slight shift to this first line here. Then it is going a constant value. Then again we are getting an exothermic reactions occurring. Then again after some it is getting constant, more or less there is no change. Then again it is an exothermic endothermic reactions. Okay, so that means each and every case we see with the standard value. Okay, so we have standard material for calibration. You can see we have different materials we use in our standard as a standard, as a reference material, so that every reference materials will give us a specific temperature value and actually enthalpy change of melting. So the melting temperature this, but how much enthalpy change required for melting this material is 120.6 joule per gram. Okay, so that means what we are trying to understand, the quantitative information of the system or the samples, how much it has required as an or maybe you can say the heat enthalpy change into the system, so that the whole material would be converted into a new material, or it can change to a different phase. Okay, so that is what we are trying to understand. So determination of melting temperature by DSC. If you just see here, that means this is the melting temperature, but where to put it? In this side, this side, this side, anywhere you can put it, because it is the highest point, but this may not be correct every time. It may not be so homogeneous or so symmetric in terms of nature. So if we heat our polymer at TC, okay, so eventually crystallization temperature, we will reach another thermal transition called melting. Okay, so when we reach the polymer's melting temperature Tm, this point, the polymer crystal begin to fall apart. That is, they melt. When the polymer crystal melts, they must absorb heat in order to do so. So that means we discussed about the crystallization or melting. Melting means your structure is completely changing from one structure to another structure. So that means you require much heat input into the system so that it will completely break. So here it is very symmetric, so that's why you can pinpoint a temperature. But this may not be same for every cases for so many reasons. I'll just show you one graph here. Okay, so if you see, so here how we would judge where the actual temperature is. Okay, so here you can see we are getting a different graph and slope is not properly fixed. Okay, so in modern DTA instrument, the sample temperature is not directly measured by thermocouple junction in contact with the samples. I discussed earlier also. So thermocouple is slightly away from your sample holder. Okay, so maybe very small difference, but it is away from it, but in contact with the sample holder. Okay, so not with the samples but with the sample holder, that means where it has been hold over the sample holder. Okay, so that's why you see there may be slight difference. So if you see this, a sample temperature and in the exothermic process, if you see, it is ideal. Ideal means when we are measuring a actual melting of a of a material. But if you actually do it, okay, so it is coming here. So due to some disturbances into the system, due to the difference in the maybe in the heating system, it is now coming here. So here what it is the actual with the sample data. So how to do it? So composition, so comparing peaks from both the figures. So once you compare, this is actually in the system real and ideal, and here is the actual system in the DSC or DTA graph. So comparing peaks from both the figures, we can conclude that the intersection point best represent the melting temperature. So the intersection points of this line and this graph. Okay, so that can, so here you see the straight line and a curved line, but here you see this point and this point. Okay, so the intersection point here. So this may be the, so as the earlier graph is symmetric, we can keep the top point may be the real melting temperature. Okay, so then determine the crystallization temperature. The similar way we can also determine our crystallization temperature. When we are crystallization temperature means the actually you required heat input or exothermic process. When it is crystallizing, the system is going to a minimum energy system. Okay, that means it will be an exothermic process. Okay, exothermic process, that's why you will get a temperature. So you see each and every graph is slightly different. Somewhere exothermic is in the below direction, somewhere exothermic is top directions. Okay, so whenever you are analyzing, you should be very careful what actually we are trying to understand. Okay, so what is happening, that means the DTA and DSC graph are giving us certain information regarding the phase change. Okay, so transition temperature, you can also see there is a slope change right from here to here. So this, that means what is happening actually, that means the internal structure is changing. The internal structure of the system is completely changing. That's why we can properly measure. And what temperature we are fixing for the transition, because you see it is starts from here and it ends here. So that means there is more heat flow. There is an increase in the heat capacity of the polymer that happens because the polymer has just gone through the glass transition. Because of this change in heat capacity that occurs in the gas transition, we can use the DSC graph to measure the transition temperature. So this is what is started, it has been ending. So we can consider sometimes in between, or maybe the complete change of your transition from one phase to another phase. Okay, so this is now phase transformation. So this is another interesting part which we really I wanted to discuss it. So DTA and DSC curves are sensitive. So what you see is a monoclinic, rhombohedral, cubic, liquid. That means this is displacive. One is reconstructive type of changes. That means one is completely changing the structure from, or maybe phase from solid to liquid. But in this case, what is happening, the reorganization of the structural pattern is happening, and they are now changing in the solid form itself. So it is not melting. but they are changing their system. This is actually a carbon tetrachloride. Tetrachloride. Initially, you see this temperature. So from light from liquid, it is now changing in lower temperature. So you can see the operating temperature can be extended to the cryogenic range using the proper cooling medium. So what that means, we try